Hello everyone, welcome to Ilustraca. In this lecture, we are going to see how we can use Teng's chart for finding out the modified pressure in foundation when foundation has loss of contact. I mean, foundation is not in contact with the soil, or some part of the foundation is not in contact with the soil. So let us understand how we can do that. So you can see here, let me just, yeah. So we can see here, this is one example, a random example I have taken. Okay, a foundation of 2.5 meter by 2.5 meter. So we are considering this as x dimension Lx, and we are considering this as y dimension, which is Ly, right? So and the foundation thickness is 0.4 meter thick. So we have you can say taken some random external force value, or you can say the load on the foundation value. So P, these are, remember, these are working loads. So P is equal to 150 kilonewton, My and Mx, right? So moment about y-axis and moment about x-axis we have taken 75 kilonewton meter, right? So if you want to find out the total vertical load is obviously the load from the superstructure or on the foundation plus the self weight. Overburden we have not considered here. Okay, so this is the total vertical load. So we are getting a vertical load of 212.5 kilonewton, correct? So now if you want to find out the pressure in general case, how we'll be finding? So my pressure Q is equal to, we know, P by A for the vertical, then plus minus mx by zx plus minus my by zy. So if we keep all plus, then it will give me Q max, and if we keep all minus, it will give me Q mean, right? So we found out here Q max and Q mean, and this is as per my linear analysis, right? This is as per my linear analysis. Now let us understand one concept which I have already discussed. So those who are watching this lecture in on my YouTube channel, so this lecture is part of my course, Structural Design of Foundations as per IS code. So this is available online on our platform Ilustraca. Okay, so we have extensively discussed these calculations in our course. We have also discussed how to perform the analysis in you can say software programs, and we have compared it with the manual analysis. Okay, so let me again discuss this particular part only for those who are watching this in our, I can say, YouTube channel. So you can see, suppose this is my sorry, let me just draw it properly here. So suppose this is my foundation. Okay, I'm drawing the cross section, and I have the you can say column, and I have some load and moment. So this moment in both direction, actually, in our case, correct? So now the thing is due to this moment, what we have calculated from the linear analysis, that suppose this is my foundation line. So we have calculated that there is some negative moment, negative pressure also. The pressure diagram is something like this. Okay, so this is my pressure diagram, right? This is my pressure diagram. So we got here minus 23.6, we got here plus 91.6, right? Kilometer per meter square. Fine. Now the thing is, remember, I am drawing it in a one line, but these values what we got Q max and Q min is due to the two directional movement, biaxial movement, correct? Anyway, just to explain you here. So in this case, what we considered, that something is resisting the you can say this foundation to go up. That's why we are getting this negative pressure value here. So generally what we consider first, we consider that suppose this is my foundation, and we consider this foundation is supported on some spring. Okay, this is foundation is supported on some spring. That means we are idealizing the soil as springs, right? Now when we say only spring, so if we apply a force vertically downwards, right, it is downward, so we will see compression in this springs. Okay, for case 1, subjected to case 1. And we have, when we have you can say force which is upward, right? So I will just write it here, upward, let me make it as 2. So we will see tension in the springs. for the case 2. So it will compress and it will also expand, right? When we are saying it is a spring, so this is the linear behavior of a spring, but the soil does not, you can say, provide any resistance, or we cannot see any tension in the soil. So when we have upward force, it will not try to restrict the foundation with its at its base, right? It will not, you can say, restrict the foundation base here to go up, right? So what will happen? In real scenario, the soil is not providing any tension in the foundation. I mean, not providing resistance against the tension. Sorry. Okay. So soil is not providing resistance. So that means we can say these springs are compression only springs. So we need to consider these springs as compression only springs. So what will happen? The soil, when we are providing, you can say, compressive force, then it will try to resist that compressive force and we will get some pressure as a reaction. But when we have tension in the foundation, we will not get any reaction. So that means this is my tension, right? And this is compression. So that means this curve that, I mean, or you can say this pressure diagram that we are seeing, it is not exactly true. Okay, not exactly true. So that means we are expecting a pressure diagram which is something like this. So if we say this is my Q max, okay, so we are expecting a pressure diagram which is something like this. Okay, so here, if this is my Q minimum, so in real scenario, Q minimum will be 0, and this Q max, it will be Q max modified. Why it is modified? Because due to this non-linear behavior, due to this compression only behavior, or due to the uplift of the foundation, certain portion of the foundation, what will happen? This compression at the other side of the foundation will increase. Okay, so we call it as modified pressure, right? So when we have this, you can say, scenario in one direction, okay, so in this case we have direct formulas in different books you will find. But when we have the, you can say, moment, the biaxial moment, and due to which the, you can say, uplift, the pattern of uplift also biaxial. So in this case, generally there is a very common use of this Teng's chart in the industry. So to find out this modified pressure and to find out how much portion, suppose this is my foundation, right? And I have moment like this, I have moment like this. So we know by seeing the direction of the, you can say, foundation, we can say that suppose this is my mx, this is my my, right? So due to this mx and my, obviously this will, and this you can say part will be under highest compression, and here the pressure will be the lowest. So we can say this particular area can go under loss of contact, right? So maybe something like this we will get as a pressure diagram, or you can say, sorry, the uplifted area of the footing. So that we need to find out, right? So to find out this, and to find out how much area of the footing is under loss of contact, and how much, and what is the modified pressure, what is the maximum pressure that is developing due to the uplift in the foundation. So for that we use the Teng's chart, which is this one. Okay, so W.C. Teng has written a book for the foundation analysis, and in this book we will find this chart, Teng's chart, which is for biaxial, you can say, when foundation is undergoing loss of contact and it is biaxial. Okay, so or you can say, we also can say biaxial eccentricity. So now here, let me just zoom this a bit. Sorry, I don't know what is happening. Yeah. So if you zoom this particular chart, you will see that we have this x-axis and y-axis, and horizontal axis and vertical axis, and some point values. Here it says the solid curves gives us the values of K. So what does it mean by K? What does it mean by K? So if you just go down here, if you see the case 1 that is given in this particular table is the general case when we do not have any loss of contact in the foundation. Okay. The part 2 is the case which is the main you can say focus for us. Okay. This part 2 is the case where we have loss of contact in the foundation, but this loss of contact is within this particular range, this box. So around 25%, you can say 30% loss of contact is there. 25% of the total area of the foundation. Then we have this case 3 and case 4. You can see case 3 and case 4. So we do not allow this much you can say loss of contact in the foundation in general condition. Even 25% is also very high, especially when you have equipment supported foundations. So in this case, I mean foundations which are supporting equipment. So in this case, the tolerance used to be very less. So you need to carefully see how much you can apply. I mean you can allow in the foundation, right? So what we were discussing that this case 2 we will be focusing on, right? So if you see the case 2, the zone is this particular zone. This is the case 1 zone where there is no uplift, and this zone is mainly my case 2 zone. Okay. First of all, we need to find out that what is the modified pressure, and for that we need this K factor. So how will be finding this modified pressure? This modified maximum pressure will be K into your total vertical load divided by your total area of the foundation. Okay, simply doesn't matter what moment you have, because this K you will be finding out based on the eccentricity of load due to the moment. Okay, so here you can see this EL by L, EB by B. This is nothing but the eccentricity which we'll be finding out from the moment. So this E value we need to find out using the formula M by P, correct? So if I just go to this formula, my whiteboard here. So if you see along my X direction, my eccentricity will be mx by P. So 75 by 150. Similarly for my also, as these values are same, so it will be 75 by 150. So I will write it here. My Ex equal to mx by P equal to 75 by 150, which is equal to how much? Let me just remove this. So which is equal to how much? It is equal to, let me, is 75 by 150. So we are getting a value of 0.5, correct? 0.5. Is it correct? M by, sorry, not 150. P value is 212.5. I have made a mistake. This is actually not P, this is PT, the total vertical load. So I need to just change this. .5. So which is equal to 0.35. We can say 0.35. Similarly for EY also we have the same, MY by PT. So it will be 75 by 212.5. So we are getting 0.35. Correct? Okay. Now once we get this EX and EY, now as per this chart I have to compare with the total length and total width, right? So EX by LX in our case and EY by LY we need to find out. So if we find out EX by LX, so how much we are getting? Our LX and LY both are 2.5, so 0.35 by LX is 2.5. How much you are getting? So 0.235 divided by 2.5. So we are getting a value of 0.14. Similarly for EY by LY also it will be 0.35 by 2.5. Okay, right? So it will be 0.14. Right, now what we can do, we need to plot this 0.14 line in this particular diagram. Okay, so here you can see it is 0.1, 0.2. So obviously this center line is 0.15. So our 0.14 will be somewhere here. Here also 0.14 will be somewhere here. Let me take a line here and suppose 0.14. It is just approximation. You have to you can say make an approximation here by seeing this gap. So from 0.1 to 0.5 you have to divide it into segments. So suppose 0.1 is coming somewhere here. Sorry, let me just draw a line like this. Okay, right? So this is for ex by lx, right? So this value suppose 0.14 we are saying. Similarly for ey by ly we will be finding out somewhere here. Let us say somewhere here. Okay, fine. So now if you see this intersection point that we have just drawn here, this intersection point, so our first aim is to find out the k value, right? So this intersection point, if you see the solid lines, we have two solid lines. In between this we have this intersection point for the ex by lx and ey by ly, right? So if we can assume another line like this here, I'm just roughly drawing another line like this here, a solid line. Okay, but actually it will be a solid line like this. So this line will define my k value. So it is somewhere in between 2.5 to 3. Okay, and it is very close to 3, and you can say it is around 2 point. So suppose say this value is around 2.75 to maybe 2.8. Correct, right? So if I just remove this, I can say that this value that we are getting here, let us say this value that we are getting here from there, sorry, it is too big. So let us say it is for k equal to 2.8. okay, let me just make it very small. Okay, so this value, I think it is just rotated. Let me just remove it. So remember what we are saying is that this value that we are getting here, this value that we are getting at this particular point, so from that if you find out the k value, let us say k value is around 2.75 to 2.8. okay, so for now let us consider it is as 2.8. so I will just write it here that from, so you understood how to take the k value from the Teng's chart. Why this k value is required, I will just tell you now. So from Teng's chart, k is equal to suppose 2.8. okay, k is equal to 2.8. now let us come to the next point in this table. So we've already seen that the modified pressure that we should get, it should be k into my q by bl. Here we have written, so it is basically k into pt by lx into ly for us, right? So if you just want to calculate it here, so in our case the p max modified will be 2.8 multiplied by 212.5 into divided by 2.5 into 2.5. so how much we are getting? We're getting a value around 2.8 into, you can say, 212.5 divided by 2.5 into 2.5. so we're getting a value of around 95.2 kilonewton per meter square. So actually when we have this loss of contact, the pressure that you have estimated from the linear analysis, it will not be the same, it will be increased and it will be around 95.2. okay, this is an approximate value because we have also approximated this from this diagram. Okay, so you can say this will be around 95.2, the modified pressure, and obviously the minimum pressure will be 0 because there is no this side the foundation is not under in contact with the soil. Okay, so we are seeing, I mean, it is experiencing loss of contact, so minimum pressure will be 0, correct? Okay, now how to understand that how much area of the foundation is under loss of contact? So this is my foundation, this is my foundation. Okay, so how to understand that how much area of my foundation is under loss of contact? So if I just divide this into 4 segments like this, it is very sure that from my moment is something like this. Okay, so it is very sure that if I just divided these segments into 1, 2, 3 and 4 like this, so due to this moment, due to the P, if I say due to P, the first case I am saying, suppose first is P, second is mx, third is suppose my. Okay, so due to the first case, we will have compression here, we will have compression here, we will have compression here, we will have compression here. Due to the second case mx, which is this one mx, if you see by seeing the direction of the moment itself, we understood that these two you can say areas, area 1 and 2, it will be under tension, so we can say tension and tension, and these two will be under compression and compression. And from my we understood that from the direction that these two will be under tension, so I'd say tension and tension, and these two will be under compression, C and C. So you can see this is undergoing maximum compression, this is undergoing minimum compression. Okay, and if the T plus T is greater than C, then it will be going loss of contact, which is happening in our case. Now how to understand? Now we know that the loss of contact that we will get, it will be in this particular, or maybe in between these two you can say components, right? So now we need to see that how this is actually how to find this uplifted area. So to find this uplifted area, again in this particular table itself, we have this x into L. So x is the coefficient which will tell you that how much ratio or how much percentage of total length of the foundation is under loss of contact along this direction, and how much of the width of the foundation is under loss of contact by this y coefficient. So to find out this x and y coefficient, we need to focus on this dotted lines now. Okay, focus on this dotted lines now. So if you see, what we need to first see that this intersection point of my red lines, we need to see that this intersection point is closer to which dotted lines. Okay, or you can also interpret like this, that this intersection line is closer to which intersection of dotted line. So you can see the dotted lines are intersected like this. Sorry, let me take a, yeah. These dotted lines are intersecting here each other. So if I say this point, so this is the intersection of x equal to 8 and y is equal to 0.4. So like that, you need to see that my intersection of red lines is closer to which intersection point of the dotted lines, or closer to which dotted lines along x and y, right? So if you see here, my intersection point is closer to this line if we talk about y, and this line if we talk about x, right? So let me just mark this again. So my intersection point is closer to this intersection of dotted lines. So we can say this line and this line. So if you see, this is for x, like that, here you can see this is written here x, and these directions from bottom to top it is y. Okay, so if you see this left to right which is coming, it is x equal to 0.5 for me and y equal to also 0.5 for me. Suppose your intersection point is somewhere here, suppose somewhere here like this. So in your case, what will be the nearest? What will be the nearest? So you can see for here are two nearest places, this and this. But now you need to approximate, I mean, you need to understand which direction it is, close to which value. So if you see this, it is 0.7 and 0.7. If you see this, it is 0.8 and 0.7. Okay, so not much variation you will find even if you take 0.8. So just depending on your understanding, you need to choose that which intersection point is much more closer to my intersection of lines. Okay, and accordingly you need to decide. So in our case it was pretty easy because our moments were simple. So we are getting 0.5 and 0.5 for the x and y values, right? So if I just write it in my whiteboard here, that my x value, small x equal to 0.5 in my case, and small y is equal to also 0.5 in my case. Okay, so now if I want to find out that, if I say this is my L or Lx, so this is my Ly, right? So it will be x into Lx, some portion. So if it is 0.5, so it will be somewhere here, right? Half of this length. So no, not here, it will be, let me just see, this uplift will occur in this phase, right? So here it will be this length, so I can say 0.5 times my Lx, right? So it will be how much? 0.5 times into 2.5, right? 1.125, something like that, right? And in this area also it will be 0.5 times my Ly. So the uplifted area which we'll be getting, it will be basically this. If you connect these 2 points, so this is my uplifted area. So how to find out this uplifted area? You can easily find out this uplifted area. We have the base and perpendicular, so half into base into perpendicular, so you'll be getting this area, and you can then compare it with the overall area. So what do you understand from these values, 0.2, 0.3, like this? This value is nothing but it is telling you that how much percentage of your footing is under loss of contact. And you can see that our case is less than 25%. Okay, in any case we are not allowing more than 25%. So this case 3, case 4 are not of our use. We will be using only this portion of the graph. This portion of the graph we will be using. Okay, even 25% also very, very high, so we need to be very careful when we are allowing 25%, right? Okay, so now if we just calculate, okay, we have found out manually that this will be my uplifted area, and my maximum pressure that will be getting modified pressure is 95 point. Now to verify this, what I have done, I have created an FEM model in 𝐀𝐧𝐝 for the same foundation with same loading. Okay, just to show you, this is my footing. If I show you the loading, show loads, you can say I have applied a dead load of 100 kilonewton, and I have applied a show loads live load of 50 kilonewtons, so 150 vertical load and 75 moment, positive moments also I have applied. And I have this you can say footing, which is F1, which is having thickness of 0.4 meter. So if I just show you, it is 400 mm thickness, right? So I have just exactly created what I have I have done in the manual manual calculation. And if you see, I have also created one load combination, which is 1.2 dead load plus live load, correct? So now it is already analyzed, and if I just show you the pressure diagram for this is for linear analysis. Okay, load combination, I will just show you the pressure, soil pressure, apply. You can see the maximum soil pressure is coming 91.2. Remember, in 𝐀𝐴, the compression is defined with negative sign, and the tension is defined with positive sign. Okay, and in manual calculation, negative is tension, positive is compression. In 𝐀𝐴, negative is compression, positive is tension. Okay, so we'll understand that this compression is around 91.3 kN per meter square. In our case, we found it around 91.6 kN per meter square. Okay, so it is almost nearby value what we are getting. and here it is 23.62 kN/meters, which is tension, and in our case we found a tension of 23.6, which is obviously near same value, correct? Now this is for linear analysis. Now if I just I will just unlock this. I'll go to define. So I'll subgrade modulus, modify. I'll make it compression only. Okay. I'll go to define load combination. I'll also change this to nonlinear case. So I'll go to edit. Let me see. Define, convert load combinations to nonlinear uplift case. I'll select the combination. Okay. I'll save it, and now I will run the analysis. Run analysis. Okay, so now it will take some time as I have converted the load cases into nonlinear cases, and the springs are also compression only. So now if I want to see the pressure diagram, it will give me the modified pressure. I'll select the combination. This combination is now nonlinear combination. I'll click on apply. So now you can see all this is now 0. So what we are getting as uplift, the positive pressure in safe, so it is tension is 0. There is no pressure actually, and from here the negative pressure is starting, and the maximum negative pressure we are getting is 95.34. Okay, 95.34. So if you see here, so it is also around 95.2, very nearby value we have estimated. Okay, nearby value we have estimated from the manual calculation. So now if you want to find out the uplifted you can say area properly, so suppose I will just give a minimum value of minus 0.001 to maximum, minimum value of minus 95.34 to maybe minus some very minimum value 0.001, like this. I will just give apply. So now you can see here, this is my area where I am getting the 0 value uplifted area. So if I just measure, if you see this location, the coordinate of x is 0.15, minus 0.15. So here x equal to minus 0.15, and if I see here, or I can directly measure also, right? I can directly measure also. Suppose I will just mark it up to this line and up to this line. Okay, so if I just go to here, draw dimension lines from here to this point 1.1 and this point 1.1. so around this area is under loss of contact. Okay, so for us it was coming around 1.125. here it is just a very small variation that we can observe. Okay, even the limitation, I think if you see here, we can divide this you can say plate into more smaller you can say elements, and then we may get more precise results. We need to actually do the trial and error. So here what you can see, that what we are expecting from the manual calculation and from the Teng's chart, okay, the type of uplifted area we are getting, the similar we are getting in the FEM results also, and the maximum pressure value, modified pressure value that we are getting from the FEM results is also similar to what we have estimated in the manual calculation and using the Teng's chart. Okay, so this way you can use Teng's chart to find out the modified pressure, and this Teng's chart is extremely extensively used in the Indian industry for you can say analyzing the footing with biaxial eccentricity. Okay, what is this biaxial eccentricity? Eccentricity of load due to this moment. So what we consider that there is no moment, suppose, and this P is shifted to somewhere here. Okay, somewhere here, suppose. So this is my eccentricity, suppose EY, this is my eccentricity, Ex, and what we have estimated, this Ex and Ey is basically m by p. Okay, so like that. So when we have this eccentricity from both directions, so in this case we expect a pressure diagram like this. There are different cases you can see in the Teng's chart in this table. Okay, so these 3 and 4 we are not allowing in the real scenario. We used to you can say allow up to this case 2 only. Okay, so our main concern is up to this case 2. Okay, you can also check this case 3 and 4, but you will see that the extensive area of the foundation is under loss of contact and it is not stable, right? I mean, we cannot say that we cannot allow this kind of it is a loss of contact in the foundation in the real scenario. Okay, so I hope it is clear how to I can use Teng's chart, okay, for foundation analysis. For the foundations, those are having loss of contact, right? So if you have any doubt, you can always write me in the chat. Obviously it is an approximate method. You have to you can say do some approximation from this chart and you have to verify actually. So if you do few more examples and few, you can say case studies, and after that maybe you can get some confidence that okay, these values are nearby to what we are expecting. Fine. So thank you. And as I said, if you have any doubt, you can always write me in the chat box. And those who are watching this in my course, you can always write me in the, you can say in the dedicated WhatsApp group. If you have any doubt, I will always try to solve it as soon as possible. Thank you and see you in the next lecture.